Uh, I have to check the exact name. Um, Generally, if you go and buy that of the shell, you have to ask for a strain gauge measuring device. Nowadays, there are lots of options that you can choose between uh, analog, digital,
Mm-hmm.
and all integrated with other measuring system. For example, the hardware that we got down in the laboratory for the model analysis is also included some channels for the strain gauge measurements.
Okay.
So the exact name of that one I don't remember right now.
Okay.
I'll tell you on Friday or maybe earlier. I email you the exact name. Okay, I have to go
Okay.
down to the laboratory and recheck the name.
Okay. Yeah. No, I was just curious about it.
Yeah, yeah, it is an old device. That device has a very old story. It comes to the laboratory in the early 50s or 60s.
Mm-hmm.
Okay, and we use them, or better, my professors use it for the uh, qualification of the first Italian satellite that, by the way, was third in the world going orbiting around the Earth. It is called San Marco, and
Mm-hmm.
they used to check that the pressure vessel is having the right strains, and therefore everything was in place at that time.
Okay.
That was the very first usage of that one.
That's so it's an old one.
Yeah, yeah, really.
Cool. And then in regards to the deliverables in our lab report,
Yeah.
um I know you want us to estimate the strain distribution over a beam span. So in the document that you provided us for lab number one, so we
Mhm.
found in your Excel sheet you had the strain for each of it since we weren't in the lab ourselves. So is there anything else we need to do outside of the Excel sheet besides just kind of discuss and talk about the results that was found during the lab? I mean, we
So,
have to estimate the young modulus as well, so we can do that. But
yeah,
besides that, is there anything else that we actively have to do?
yeah. What you have to do is try to see if for example, the predicted Young modulus of your um, cantilever beam, and you can predict that using the Euler-Bernoulli beam with the strain measurements and the information of the load, is the one that you were expecting. I mean, that is a light alloy, maybe aluminum alloy. So you know approximately what is the Young modulus, and therefore maybe you can predict that. Okay.
Okay.
But however, I missed to include in the Excel file some geometrical measurements, such as the thickness, the width of the cantilever beam. So I have to go down and take these measurements for you. I'm
Okay.
going to do that in let's say few days.
Okay. That
Okay,
works. Thank you.
you're welcome. By the way, next week will the fourth laboratory activity will be available. I made another recording so that you can have the information of this laboratory activity as you were there. I know that is not the same, that being in the laboratory will contribute significantly contribute to the understanding, the overall understanding of the experimental model analysis. But however, that what COVID is is giving us for this year, and therefore I think that instead of having nothing, just my recording could be giving is giving you at least a touch, a feeling of what is the experimental activity. um if I am able, maybe the end of the week I will release this recording, and therefore you can start working on that. And once again, if you have any troubles, if you need some more, let's let's say, discussion on what we did, just email me or just share your doubts and questions with all your colleagues during these classes. By the way, I hope that the laboratory activity number 3 is also okay for you. I made the recordings because I record my screen, mainly that laboratory number 3 is using the MATLAB 5. So I think that is enough what we did, and I gave you the text so that you have the reference for doing that. Okay, so once again, if you have any issues on that laboratory activity, just let me know so that we can discuss a little bit. Also with all of your colleagues. So if you have questions, just share those questions with you all. Once again, these laboratory activities are not mandatory for the final exam. Okay, the final exam is made by 3 questions. Okay, these 3 questions span the whole program that we cover from the very beginning to the very end. So end of September, if I remember well, to just the day before Christmas or something like that. And if you have if you have the laboratory activities done, so if you submit your report, let's say a week before the final exam date, and then we can you can have 1 question just on a discussion. So 1 out of the 3 questions just on a discussion of one of the laboratory activities. So it should be very easy to you. Because of the COVID, I don't think that we are going to have the exam in presence, at least for the very first month. So all the oral questions that we can have will be in a written form. Okay, so what you have to do is just write using the exam.net, if that is available, your answers to my questions. But because of the distance, I just want you to write your questions. It is not a written exam in the strict sense of the term. It is an oral questions, but you have to write that down on the sheet of paper. Okay, so having said that, let's start.
Excuse me, Professor.
Yeah.
Actually, I tried to access some lecture videos, but I'm not able to, access them.
I don't know what to do because as I said at the very beginning, all these classes, all these course notes are available in a, let's say, for a week time, 2 weeks time, maybe no more than that, because those classes are not intended for distance learning. These are just for you to have a reference, but for a short period. I would like you to have the course pace. Okay, so everything that we are going to discuss today should be reviewed in a very short time, so that you are with me following the course topics. Okay, if you are now reviewing what we did at the very beginning of the classes, that's good, of course, but that is not the scope of these course notes that I'm sharing with you. Okay, so what I have to ask you is to review immediately after the end of the course your notes with my course notes that I share with you. If there are some troubles, ask to me, and therefore all the materials is with your own once I remove that from the Google Space.
Okay, fine, Professor. Thank you.
Okay.
Will lab 3, sorry, will lab the recording from last week for lab 3, will that be up longer than a week or no?
No, I have no limiting time for the recording of lab 3. Okay. Also the text should be there. Okay, because these are referring to the laboratory activities, and I gave you full time. You can give your final exam, let's say in July, and then you still have these laboratory activities available for you. Okay, but not for the recording of the course of the general class and for the notes. Once again, it is not a distance learning, so all the material is not, let's say, packed for the distance learning activities. These are just notes that I'm writing while I'm talking with you. So as you were in the classroom with me. Okay, so it is just you have a blackboard in front of you, and then you have to take your notes. Okay. Okay, so let's start today's class. Keeping going on the model parameter estimates. Last days, we saw how to estimate your model parameters using two approaches, the logarithmic decrement method and the half power bounding method, or also called peak picking method. These two methods are have in common that they are based on a single degree of freedom model, and they operate in frequencies and time domain. The peak picking method operates in the frequency domain. The logarithmic decrement method is working on the time domain. Now, let's see what happens when we are removing that hypothesis, and we consider your whatever system characterized by more than one model parameter that is important, that is affecting your response in whatever point of your frequency range of interest. Okay. Before doing that, I would like to give you some remarks concerning the effects of the residual terms. Okay, we already introduced the residual terms. Now let's see what could be this effect. So let me write that effect of the residues, that are the residual terms when we are referring to our analysis. Okay, what does it mean there? It means that we are evaluating your frequency response function in a given frequency range. Okay, and because of that, we are just looking at your system dynamics only through the effects of some modes, unlimited number of modes with respect to the infinite number that we can have when referring to an infinite frequency range. Okay, so your FRF known in a prescribed frequency range. Okay, in which only, let's say, m modes are present. Okay, so when we are resynthesizing your FRF from your knowledge from the mode shapes, this FRF will differ with respect to the, let's say, the ideal one, the good one. Okay, so the synthesized FRF, that is the FRF built on the knowledge of the estimated modes. Okay, some errors. This is the FRF, sorry. We have some errors. Okay, that is in general what we do. An effect of that could be viewed just by looking at this plot. We have omega. We have our, for example, amplitude of your FRF, like this. Okay. that is your ideal FRF, for example, that is known just at prescribed points like this. Okay, so these are your experimental points. Okay, and then, for example, what you got is your FRF that is, let's say, having this behavior when you are not considering any residual terms. So that is your FRF without residues. Okay, if you add your residual terms, maybe you can have your FRF that is practically the one that we are having when estimating that using the, let's say, H1, H2 estimate that is from the experimental points. Okay, so this green line is the synthesis with residues. Okay, so this aspect is very important. So every time that you have to characterize your system, the first step is to identify, of course, your model parameters in terms of natural frequencies, damping ratio, and shapes, but also don't forget to estimate your residual terms because that is the overall effect. You have the blue points that is representing, if you want, the truth, if you want the experimental vision of your system dynamics. If you use just the modes that you have identified, your model parameters they have identified, you have the red line that is quite a good approximation, but is completely missing the effects of the residuals, okay? If you would like to have a good representation of your actual experimental system dynamics, then you have to add your residual terms, and therefore that leads to the green curve, dash curve, that is practically overlapping the points, the blue points representing the experimental investigation. And that is because, once again, your residual terms could be introduced by the fact that you are analyzing, indeed, you are viewing the system dynamics from the eyes of only the modes of interest. So generally speaking, your Hij, your frequency response function referring to an output and the input Ij as a function of omega could be viewed as the summation sign, okay, from R that goes to the first mode up to the last mode that is available in our analysis of your residual terms, Aij of contribution to the R mode, and then omega and R square negative omega square when we go the damping factor J eta R omega and R square. Okay, and you're using this equation instead of using this more comprehensive equation that this is one. Summation sign from R that goes from 1 to M1 negative 1, okay, of everything. Okay, I'm not writing that. Plus the summation sign from R that goes to M1 to M2. Everything is the same. Plus the last contribution R that goes from M2 plus 1 to infinity, okay, of the whole contribution. Okay, we already discussed these three contributions, okay. These contribution, go back to your notes, I'm not going to do that right now, is represent the effect of low modes, okay, that are proportional to the mass line, okay, so 1 over negative omega square, and then the corresponding mass acting at those frequency. Okay, and those low frequency modes are affecting what's happening at higher frequency, as you can see from this summation sign. Okay, and therefore these are what we are having, the upper residuals. On the contrary, this last term in the summation, okay, is representing the high frequency modes, okay, that are proportional to the stiffness line, so 1 over kJr, the flexibility actually, okay, and these are the contribution of the lower residuals, okay. And therefore, if you now plot everything together, you can have a plot similar to this one. So let me have this kind of plot. I'm always referring to the amplitude of your FRF, whatever it is. Okay, so we got omega here. 2, 3, and for example, this last line. So here, for example, what we can have, if that is our frequency range of interest, what we got is that maybe we are missing something like that, and that is what's happening to the low frequency contribution. Then, for example, in the right frequency range, we are having this one, okay, and it is what we are having without any introduction of the residual terms, okay. That is now that I'm going to write is the effect of the higher frequency mode, something like this, for example, okay. So if you add everything, what you got is the right representation of your FRF, for example, this one. Okay, that is the truth. That is given you by the low plus the actual without any residual compensation plus the high frequency term that I just completely forgot to write. I'm going to write it now. Okay. And it is high. Actual plus high. Okay. So if you just have a synthesis of your FRF with the modes that you estimated in the frequency range of interest, you have just the information of the actual FRF. That is not true. That is, there are lots of differences, especially in the amplitude. Okay, if you put the effects of the low and high contribution, so low frequency and high frequency contribution, that is the residual terms, then you can have the actual FRF. Okay, just a last word on these residual terms. Both the lower residual and the upper residuals are, sorry, are identified by an iterative procedure. Okay, and this iterative procedure is first, what you are doing is evaluate your Hij at lower frequencies. Okay, to found the lower residual terms. Okay, and then second step, the FRF is evaluated at higher frequencies. Okay, to found the upper residuals. Okay, the third step is lower residual and upper residual are summed to your Hij, and then go back and then iterate to the first step until convergence. Okay, and the convergence is done when the convergence criteria is met. Okay, for example, you have whatever small quantity that could be the difference, the norm 2 difference between your Hij that is experimentally evaluated, that is H1, H2, negative your Hij that is evaluated with your receiver, for example, norm 2. Okay, and therefore you can have the estimate of your residual terms, and there you have everything in place. Okay, so having said that, or if you want, having pointed out the importance of being of evaluating your residual terms, lower and upper residual, let's see now a general multi-degree of freedom approach, okay, in the frequency domain. So let's start with this one. So general approach. Okay, that is based on a multi-degree of freedom approach, and that is operating in the frequency domain. Please note that there are many possibilities of implementing this general approach, and all these possibilities are proprietary with respect to the software houses that are operating in the model analysis. So what I'm giving you now is just the general approach. Okay, so this general approach starts with your measure FRF, okay, your what we call the experimental one. So you know your FRF when you are exciting the system at a given J degree of freedom, and you are measuring the output at a given I degrees of freedom. You know this frequency for whatever frequency lines available in your analysis. So you know that at the L value of the frequency, and we can call that as the measure one, okay? Measure means, for example, H2, H1, HT, whatever, okay, estimator that we use. And this measurement, this measure FRF, sorry, could be also rewritten in terms of HLM, just to reduce the number of indexes we are considering, okay? And this is your reference. Then what you got here is the same FRF HIJ that is referred to the same L frequency line, okay? We can call that as HL, and this HL could be viewed as the synthesis of your molar parameters. That is -1 over omega L square Mij, the mass that is operating in that frequency range, plus the summation sign of R equal to from M1 to M2, and then the residual terms that refer to the same indexes Ij of the R mode, and then omega N R square negative omega L square, then J eta R, and then omega N R square, okay? And the last contribution is here 1 over Kij, okay? That is the flexibility. So you are guessing your FRF, okay, by using this equation that you know very well. And this is, okay, at the beginning, you can use the peaking method, for example, okay, as initial guess. Okay, so we don't know actually what are all these parameters, but you can start, for example, using the peak-picking method. Within the peak-picking method, we don't know anything about the residual terms, so you can set these values equal to 0, for example, so the lower and upper residual are set to 0, and then you have just to introduce your mode shapes, that is the residual terms, the natural frequencies, and the damping ratio or damping factor, as I wrote here in this equation, just to have a starting point, okay? So your unknowns of the problem are, as you already know, the modal parameters, so the residual terms, Aij of the R mode, the natural frequency, omega N R, the damping ratio, eta R, okay, and the residual terms in terms of the Kij, the ridge stiffness, and the corresponding mass, okay? By the way, what we are having is that these first three terms are all defined in M1 up to the M2 indexes, okay? So there are a number of modes that are included in your analysis. So these are the unknowns, of course, and you have to find out those unknowns so that you are having the synthesized frequency response function, Hij, that is equal to the measure frequency response function, Hij, as well. Okay, so how can you do that? For example, you can define the error for each frequency line available in your analysis as the difference between these two values of the FRF. So the error for each frequency line omega L, okay, is defined as epsilon with the index L of H L M negative H L. Okay. Because we are having many possibilities in choosing the coupling IJ, that is the couple, the pair of input and output, these are vectors. So you can broadcast all this information for each vector. Okay. So we are having the epsilon is a vector of error. Okay. And H, of course, is a vector as well. Okay. So these are vectors, okay, whose components, oops, oh, I don't know what happened. So whose components are referring to the measure degrees of freedom. Okay. And therefore what we got here is the resulting errors, okay, for each frequency line is a vector that is generally a complex quantity whose dimension is n output times n input, okay, and then 1 because we have just one column, okay. Therefore, because we are having a vector that is representing the error at that frequency line L, okay, let me write that better. Yeah, omega. Okay, we can evaluate a scalar form of that error. So the corresponding scalar form of the error is capital E L, that is your whatever norm of the previous error L vector. Okay, for example, norm 2. Okay, and this is a scalar form, okay, that is evaluated for each frequency line okay, and of course considering all the NO times NE degrees of freedom. Okay, now we can move from this error for each frequency line to just one scalar, okay? Considering now all the frequency lines, we are having that your error E, it is the average, for example, and F from L that goes from 1 to N F of your E L. B and F, as you know, the number of the lines that are available in your analysis. Sometimes, by the way, it is also recommended to introduce some weighting scalars in order to give different importance to those frequency lines that are giving the true information with respect to the other frequency lines that are not giving any information at all, or maybe they are introducing some noise. And for example, this information is ready available when looking at the coherence function, because through the coherence function, we know what are the frequencies in which the coherence function is low, and therefore the signal to noise ratio, for example, is very, very high. We can think to not include those information in your estimating procedure. Whereas there are also looking again at the coherence function, there are also some frequencies in which this coherence function is very, very high, and therefore they are giving us the true information of your system, the true contribution to this, to the estimating procedures. And therefore we can have, okay, this equation written in a different form, okay, it is in order to give more or less, of course, importance to some frequency lines. We can rewrite that error, okay, as E equal to 1 over F. It is always an average. Then the summation sign between L goes from 1 to the number of frequency line, but this time we have some weighting function. For example, WL, then EL, okay? And that is a weighting function, okay? And that is the final result that we can consider, okay? So in order to start our estimating technique, we have to refer to this quantity, this capital E quantity, that is telling me what is the general difference with respect to the measure quantity in terms of FRF with respect to the one that I already estimated, that is the one synthesized by the Mose shapes that are our unknowns. So in order to have this quantity that is going to zero, that is, we are having the synthesized FRF, the HIJLF of omega, that is practically equal line to the one that we already estimated with H1, H2 estimator, we introduce a sort of minimization problem. So all the unknowns the unknowns, it is your model parameters are estimated by solving the minimization problem of E. Okay, you would like to have your error minimum 0 if possible, and that is done by solving this equation. The E over the QI should be equal to 0. Okay, in which, of course, your QI are, for example, let's see, Q1 is the first residual, so A two, and so on. Okay, go down, okay, to the number of unknowns. Okay, what we got here is a system of linear equation, linear system of equations, sorry, non-linear, non-linear system of equation, okay, with unknowns Qi's, okay, that is your Qi's are having the meaning of the model parameters, that is all the volume residuals, natural frequencies, damping ratios, and so on. Okay, so all the methods could refer to this basic equation, and of course the way these methods are solving this basic equation is completely different from one software house to the next one. Say so, we are differences like there, but however, the solution is given by the solution in terms of model parameters are obtained from this equation. So what we can say is that first, different solution algorithms okay, with respect to a solution sequence, okay, most of the algorithms are iterative. So they start with one guess and then start iterating until this error is practically zero. But the most important thing is that all the methods, oh, sorry, okay, are dependent on the initial guess. Okay, I already talked about that. This initial guess could be the modal basis that you can have by applying the peak picking method, but there could be also some other techniques that are evaluating this initial guess by their own with some other analysis. Okay, so what we can say, accuracy will vary. Okay, accuracy in the estimate. Okay, so that's it for the multi-degree of freedom based estimating technique that are operating in the frequency domain. So the most important thing to remember is that those methods that are generally iterative based methods are based on the minimization of the error between the measure, that is the H1 and H2 FRF, and the synthesized FRF, that is the FRF obtained by using the model parameters that you would like to have, okay? And this minimization procedure, that is an iterative one, requires an initial guess. And this initial guess could be from the peak picking or other methods. And it requires a sort of minimum criteria, and that is dependent on the solution type that we are looking for. All software houses are developing their own code. So if you are interested, you can develop your own code. And if you are lucky, you can have a lot of money by producing model analysis software, okay? Just by looking at that. Now, let's have a 5 minutes break. So let's see now, let's say you are free before 3:10, okay? If you have any question, of course, I'm here.
Professore, ma nel vettore delle incognite qui sono comprese anche le pulsazioni e i fattori di smorzamento?
Sì, sì.
Ok,
In
quindi sono visibili.
the Q vector, there are all the modal parameters. So I'm scrolling, yes, here, all the modal parameters that are here reported. Okay, the unknowns are everything.
Grazie.
Prego.